All right, hi everybody. Thank you very much for providing me the opportunity to be here to talk a bit about a piece of my research and my PhD thesis. So the title of my talk is Devils in Diffusion, and this will be an introduction to diffusion-based generative AI and some of the backdoor attacks that happen in them. Before I begin, I did want to start by plugging the Cyber Range, which is a new place within the University of Ottawa. Some of you might have been there before. Recently, SIMT had a meeting, an event that was held here. But beyond being a wonderful place for tours and gatherings and meetings of that sort, it is also a cyber incident response training facility. So they have undergraduate and graduate students doing simulated responses to perhaps any sort of number of cybersecurity incidents to get them exposed to rapid response to events that might happen at any individual company. And my professor here is as well, so this is a fantastic place. So if you're looking to get involved in more of the cybersecurity aspects of any of those domains, the Cyber Range would be a wonderful place to get in contact with. A little bit more about me in particular. As I mentioned, I am a PhD candidate at the University of Ottawa. My background, I always hesitate at least a little bit in saying that it's in metaverse, because that was a term that kind of existed after a crypto and NFT hype, and then the metaverse was going to be the next big thing, and then it just kind of didn't happen, and then AI blew up. So I say that with some hesitation, but people are still working on that concept. It's still a very powerful concept, and I think that with some more inter-domain collaboration, we will be able to bring the goals of that idea to fruition. Specifically within that, I work mostly in backdoor attacks in neural networks and generative AI systems, and I will explain a little bit more about what those mean throughout the presentation. I am also very much interested in leveraging synthetic data from these Gen AI systems for something downstream, so training an AI system within simulated environments. Maybe these generative AIs are able to make textures, or they're able to make 3D models in which an AI reinforcement model might be able to explore that environment. So trying to replicate real life without a tedium of manual creation of these environments. I work with secure federated learning systems, so that would be like how you're able to learn from your text message changes. When you're editing something on your phone, you kind of are providing some information back to this model that can help to autocorrect without sending every single character you input into your system to a third party. So it can learn on device, and then you federate all the neural networks from the devices on some central location, so we can all learn from everyone's data without sharing the data directly. That's the goal of the system. And I also work with mixed reality and virtual reality applications for training procedures. So I'm using some of those outputs from the synthetic data to create scenes. I've done it with manufacturing, where they have a complicated process and they try to train the user using mixed reality or virtual reality solutions. And if time permits in my thesis, I would like to explore if those training facilities are incorrect, if there's some missing data or something is wrong in the application, what kind of impact does it have on your trainees downstream? And like I said, I do try to apply everything that I do in my research to some form of practical application, so it's not just theoretical, and it grounds me in actually providing something that someone would use at some point. So if you're interested in anything that I talk about throughout the talk, you can reach out to me directly for future collaboration. For some of the more general cybersecurity applications you're looking to collaborate, there's the link to the Cyber Range, or shout out to my wonderful supervisors, Dr. Paul LeBranco, who's not here, as well as Dr. Guy Vincent Jourdan. You can email them as well. So today's agenda, this is going to be a brief introduction to the state of attacks on diffusion models. So I will do some information on generative AI in general, with diffusion models being the main focus. So we're going to open up the hood a little bit to see when we say these terms, like what is technically happening behind the scenes. I'll then introduce what a backdoor attack is on neural networks in general, then apply that to backdoor attacks within these diffusion models in particular, and then finally introduce a part of my thesis, which is called devil diffusion, which is a more subtle and I think more powerful attack on the diffusion models than what has been previously done in the research. And I know people don't really like to raise their hands for questions, but I do have a few things that will help me guide throughout this. So who here has used a diffusion model before? So this is Dolly or Midjourney, or these types of things. Okay, a good number. All right, how many people have ever trained a neural network in any fashion? Okay, some. Has anybody ever trained a diffusion model? One. Yeah, maybe? Maybe. Okay. All right, so I think this will be not very math intensive, not super technical, but I think there's going to be something in it for everybody to get out of it. So we've already kind of talked about this from yesterday's talks and as well as this morning. So Gen AI, when I say the term, I refer to relatively recent developments that come from large neural networks that we perceive as quote unquote creating new content. Some people make the argument it's not really new, it's just a regurgitation of things that's already been trained before, but to our perception, it is novel in some aspect to how we consume it. These refer to, there are text-based systems, of course, ChatGPT being the most popular. Many other large organizations have their own. Bard, Claude, Grok are some other examples. The image-based systems, where I typically do most of my research, some popular ones are Stable Diffusion, Midjourney, and DALL-E, also by OpenAI. And then there are some also music-based ones, naughty ones that Suno from yesterday night. They're a lot of fun too. But for the most part, throughout this talk, for this talk, I will be doing the image-based systems of generative AI, so that's where I'll be focusing. So as a high-level overview, using words, what is a diffusion model? And a diffusion model is basically a neural network that learns to model some distribution of images that it was trained on by denoising those images. So it starts with a noisy, that looks like pure noise, and it steadily, step by step, learns to remove the noise that gets back to the original image. And we'll go a little bit more into each of those steps, but a neural net, if you're not super familiar with what technically a neural network is, the way I think of it is think of hundreds of thousands, if not millions or billions of little knobs, and they're all connected to one another. So you put in some input to this system, and you want it to say 1 or 0, or somewhere between 1 or 0, and the correct answer is 1, so it goes through all the neurons, and as they're connected, they all have little values that you can tweak, 0.8, 0.7, negative 0.1, connecting each one, and it gives out, the correct answer was 1, and it gave out 0.9. Well, you can do some calculus. If you'll learn the slope of each error between each connection, push that error back through every single one of those things, and you take a little turn of each knob, and you put that same input in, and it's going to be 0.901. It'll be slightly closer to the correct answer. And you do this over and over and over a massive number of times using gradient descent in small steps, and eventually, throughout all of your batches, throughout all of your inputs, you eventually learn to model, you end up having the ability to express that function throughout this large network. So that's simplified what a neural network does. When I say distribution, I just mean it's whatever you are able to feed into the training set of training those little tunes. It is ultimately able to relatively well represent that distribution of images that it was trained on. And by denoising, we'll see, it's the process of, I like to think of it like a sculptor, how it starts out with noise essentially as the main block that you work with, and you chisel away little parts of it, and eventually it looks like whatever you're trying to create. This is kind of like the same type of process, but with pixels. It learns how to remove a little bit amount of noise in each single time step, and you eventually get to an image that you were trying to generate. That's typically what they look like. That's the neural nets there on the bottom right. That's the part there that I was saying that each one of those little circles would be connected, if you're able to see that. There is, of course, a natural language component to it for the most part. I won't be delving too much into that. For the most part, these diffusion systems tend to be more tokenization. As we'll see, they don't necessarily understand the text that's input into it the same way that perhaps a large language model, something dedicated to, in fact, understanding text would do. But there is a tokenization component where whatever text you try to put into it helps steer the reverse diffusion process to generating the image of your choice. So the architecture that typically drives these is called a U-net, derived from its wonderful U-shaped. It's relatively simple, all things considered. Some of the large language models can have dozens of different types of specified layers within the network, but diffusion models in general, some of the basic ones, have relatively few types of network architectures here. So convolutions, it learns to extract certain features from an image, certain curves. It does this in an encoder-decoder system, so it basically goes down and it pulls out the most salient features. It compresses them down at the smallest blocks around layer 4, and then it expands them back up. So it goes down, and you have this way of compressing the image internally to the network So it understands what's important to it, and then it pulls it back out so you get the original size image that you started with. And there are also skip connections, so it's able to make inferences about what was important in layer 1 and connecting those things, that type of understanding, into the later layers in the network as well. So a little bit more technical information about diffusion as a concept. So it's a little early for math, so I'm not going to go too much into this. But what happens here, this is diffusion. So diffusion is actually the process of making them more noisy, and when you generate the image, that's actually reverse diffusion. At this point, this seems to have kind of been lost in the way we talk about the concept, but that's actually what's happening. So for the most basic of diffusion models, it's around 1,000 time steps. So you start with your clean image. This is Q sampling, your clean image on the left, and eventually you want to get over to your fully noise, it looks like random noise image on the far right. And to do this, it's Q sampling. So from your previous time step, t minus 1, you want to go to the next time step, xt. What do? You get a normal distribution of pixels where the mean is your square root of 1 minus beta t, where beta is some kind of noise scheduler and how it adds noise over time. It can be linear. It can be sort of tapered off, where it's less noise. It starts adding less noise at the end so that it's more of a slower transition to your full noise. There are tons of different ways to add noise throughout this thing. And then on the right, it's beta t times your identity function. So we just, for the most basic ones, the mean is something that you'll eventually have to learn, but the variance, the standard deviation, is something that's fixed. So then you only have to have a neural network that can learn the mean of how we've added noise to these images over time. Then we do the part that's actually a bit more of the magic. It's the reverse diffusion process. So again, if we fix that variance there, the sigma theta on the far right is not a neural net. We don't have to worry about training something to understand the variance. You could definitely do that if you wanted. But for the most part, the basic models, we just worry about learning the mean, which is your mu theta in the middle on the top line. And to do that, we model that by a loss function. So this is our loss function of x, given your image, your time step that your image is at in the noising process, as well as epsilon, and that's the amount of noise. So this neural network will essentially maximize over average, or minimize the loss, maximize the expectation, minimize the loss, between what noise was added at that time step and the accumulation of the noise over time that was added to that image. So that's, as you go forward in time steps, alpha will eventually disappear. It turns very small. So we don't actually do the full forward diffusion process when you do it, because that would require, like, if there are 512 by 512 images and you had 10,000, you had 100,000 of them, and you had 1,000 time steps, you can't store every single one of those images in memory or on disk at any particular time. So everything there past the epsilon theta is just a real shortcut way of instantly going to any particular time step without having to save all those images to disk. The short end of it is it learns how to predict little bits of noise at each time step, and eventually it is able to go and undo the entire noising process so that in the end you show it a new amount of random noise and is able to steadily remove that noise step by step to get you what it thought was the original image, and that image tends to reflect the distribution of images that it was trained on. So a totally unhinged thing to do with a system like that would be to go out to the internet and download everything you could possibly do and scrape it and throw it into the model, because then you have really no control over what this thing is going to produce, and you have essentially the ability to model a distribution of anything on the internet. So there are some shortcomings and problems with the approaches that have been done. I like to break them down into three main things. So I refer to them as inherent problems with diffusion models. These are not things that were deliberately embedded into the behavior of the model. This is just what happens when you do that train on the entire internet type of approach. And I refer to them as biases, misunderstandings, and a lack of control. So they can basically, as I said, they can basically learn just about any type of genre and style. This includes telling it to make me an image that looks like this particular artist's style, and it will go down to even replicating the signature of that artist in those images. They don't like that, obviously. That's not fair, but that is what they have done. They can also have subtle and also not so subtle biases in the types of outputs that it creates based off of your prompts. They can range from benign ones, like the one here, as well as some more severe mischaracterizations, I should say, instead of characterizations. This one was from Reddit, people really trying with diffusion models to make a cartoon nerd. That's all they wanted, but they didn't want it to have glasses. Virtually impossible. These large diffusion models do not believe that it is possible to be a nerd without glasses if you're a cartoon. And so this is a fun one. I think that, and it really tried. I mean, they tried so many different prompts to the point of being ludicrous, and it's a funny example. Some of the less funny ones would be like if you ask it to make me an engineer, and photorealistic 4K engineer, and it's going to be a white guy. Right? That's another very typical thing that these diffusion models have in them. And the responses to trying to fix them are also, they're not simple. What you can do in response to those is not straightforward. I know that Google has recently been trying to work on that concept. And so you are able, in fact, to generate more easily. If you just say, make me an engineer, you'll see all different types of engineers, different appearances, skin tones, and genders. And at the same time, they also introduced the bias of saying, make me a World War II Nazi soldier, and they will also be diverse in skin tones and ethnicities. And so, it's a little bit of whack-a-mole when it comes to the biases. So they come from this, how I refer to them as misunderstandings in what you're inputting as a prompt and what you're expecting out of them. And this comes from, one main issue with how you get prompts for your massive training set means that the captions that they assign to the images don't always reflect the reality of what you want it to. So this was, I just want to confirm that this still exists. DALL-E 2, draw me an image of without a pink elephant, and the only thing you'll get is images of pink elephants, okay? This is, funnily enough, a psychology test. If you tell a group of people, whatever you do, don't think about pink elephants for the rest of the day. If you talk to me later, don't think about pink elephants. Humans also have this issue. But I digress there. What happens with getting prompts for these images is when they scrape the internet, if it doesn't already have like an inherent caption as part of the image, they have to look inside of the text to help infer what is in this image, if it's just there. And if you have, for example, if you think of something related to elephants, if it was articles about the extinction of a particular elephant, they're going to say, without this elephant in the, this environment, this will happen. And they assign that text to this image. The image has, in fact, an elephant in it. It will learn that that text corresponds to this concept. So that is, a relevant misunderstanding that these models have based off of how the internet is scraped. There's also other ways of adding prompts to images without them. That relies on a different neural network that's been specifically trained to give prompts to images. You've probably seen this in PowerPoint where you upload something to it, and it's like, here's my accessibility text, and it has nothing to do with the image you've just uploaded. They kind of leverage those types of systems in order to add captions. On average, they're good enough, but to improve the model's performance by doing that, but they have severe limitations as well and can lead to further misunderstandings. And finally, a lack of control in what you will get out of them, and you really have no ability to predict what you'll get. This image was taken from a lottery promotion from somewhere in the States, and they said, upload a picture, like a selfie, and we will give you what you will win, what you'll do with your $1 million when you win this lottery. And a woman uploaded a picture of her face, and it was like, you're going to go to this hotel in the Caribbean, and it made her topless on this bed in a weird aquarium bed. And that's not acceptable in any fashion. So that would be, the model thinks that was what is most likely to be a representation of that scene. Since they can model just about any distribution, these things, as we'll see, they're really not ready for unfettered just distribution to the public if you have a reputation to maintain. If some of the bigger players, they can caveat you and say, you'll get what you get. Sometimes they make mistakes and then they just protect themselves. But if you're running something where you're using generative models where this would harm you to make deepfakes of someone, would recommend against not having at least someone look over a quick glance of these images before they go back to the users. One other additional complication to all this is that in modern deep learning, using a pre-trained model is the norm. That is the default, which results in even less control over the initial training data that this model saw, as well as any other unintended model behavior that might be latent in it. The reason for this is that these models, even basic ones at this point, are absolutely immense. So for my research on this particular topic, where I use a relatively small neural network comparatively on only 50,000 images, and they're only 64 by 64 pixels, using one of NVIDIA's $10,000 GPUs, it would take like 4 days in order to try out one combination of parameters I had to test, where we had 96 parameters to test throughout the research project. So that would be from training from scratch. That's where all those knobs are randomly initialized. It has no understanding of anything at all. If you start from scratch, you don't have to worry about it having seen images that you might not like. But if you do start from scratch, you'll have a much more expensive and time-consuming training process. So most people are not super concerned with the behavior of their diffusion models. So they do tend to use these pre-trained ones, and then they fine-tune them on their target task of distribution of images that they're that is relevant to them. And Hugging Face, for example, has hundreds, if not thousands, of pre-trained diffusion models on a number across all sorts of domains. So you can just go out, pick one, and be none the wiser to what images that model was actually trained on in the first place. For the most part, it's fine, but this already opaque black box nature becomes even more of a black box when you use these pre-trained models. And they have, from the beginning of neural networks, also introduced the possibility of backdoors being present in your model, which then survives your fine-tune process. So a little bit more about backdoors in neural networks. Neural networks, as I said, are extremely complex. And as a result, they are over-parameterized, meaning that they are more expressive than what the task is being required of them. In a lot of cases, if you're doing an extremely immense, complicated task, that's not true. But for mundane tasks that we might be fine-tuning these models on, they can learn much more than what we're asking them to do. And because they're black boxes, that means we don't know what they were trained on. We don't know how exactly they were trained. And we don't really know what they can do. Like, we can only send the inputs of the images that we have. If we don't have an image that represents a certain scenario, it's really hard to tell what it would do given that scenario. And this is one of the first works in this. This is from Bad Nets. And they showed that it's pretty trivial with a small amount of, like a sticky note on a stop sign. You can convince that model that it's a yield sign with very high confidence. Because in their training set, they optimized for, if it has this trigger, call it a yield sign. And if you show it only pictures of stop signs and yield signs, does fine. You don't have the particular picture with this particular symbol over top of the stop sign. It's difficult to figure out that this backdoor behavior is present in it. And detecting these backdoors, it's a manual process. So if I got an image classification model, I would have to run the suite of defenses against the model and hope that one of them actually does something. It's not like Hugging Face does this to your models when you need to go to download them from them. They're like, verified, we ran it through this suite of state-of-the-art backdoor detection methods. They typically rely on finding a minimum amount of perturbation to shift a class recognition. So for image recognition tasks, yeah, probably, not probably, the state-of-the-art backdoor detection schemes would work on something like this. But if your type of backdoor behavior is something that's not minimizing a shift from one class to another based off of pixel perturbation, that breaks down, which diffusion models it breaks down in them because that's not quite how they work. And there's kind of not really a guarantee that all backdoors were detected. They can learn dozens of different backdoor tasks depending on the complexity of the model. So if like the first 10 are easy and then some are more difficult to detect, it'll start giving you false positives on backdoors and you're like, oh, I must have got them all. So there's really no way to know exactly when to stop on detecting for these types of things. So that leads us to attacks on diffusion models. Despite the fact that diffusion models in general have been around a bit longer than you would think, around 10 years now since the first ones were really proposed. They competed with GANs for a while, which that's a separate type of thing. They can also create new images, but entirely different architecture. And from these, there were two main research areas, both from IBM Research. They're called bad diffusion and villain diffusion. Bad diffusion learns to attack from the noise space. So it learns, instead of, if given some particular trigger in the noise, it learns to generate any target image that you want, if that trigger is present in the starting noise that you want to reverse diffuse through. So in this case, you can compare the clean noise to the trigger noise on the bottom. Bottom one is bad diffusion's noise attack, so you can make this model learn to generate any image on command if you feed it this noise. And villain diffusion is the same type of idea, except it learns the correlation between a malicious prompt and that target image. So in this case, instead, when you just said cat, it will give you the cat image. But if you said cat with the cat emoji, and the cat emoji was a trigger, it would give you your desired target image. But there's two things about this, as I was doing my research in it. As I'm interested in downstream attacks using synthetic data, I'm like, well, these actually both require some sort of manual input in the attacker. This noise from the last slide, that's never going to really occur naturally. It won't. If you tell it to generate me random noise using the NumPy function in Python, it'll never make the noise that looks like the bottom left, so that will never occur. And it would be extremely unlikely that you would allow a user to provide their own starting seed of noise. You might be able to provide your own starting seed number, so that gives you different images based off of your prompt, but it's not like you would never have the opportunity to provide your own noise in this circumstance. And the prompt one, yes, that's much more possible. But for circumstances where, like for me, if I'm saying generate me textures for this platform because I made a 3D scene and I want to do randomly regenerate the scene with brand new textures, those are going to be fixed prompts. Like I generated those prompts. They're not going to have the trigger in them more than likely. So I was like, well, how do we make these things, this diffusion, happen without any input from the attacker? And so that's our work, Devil Diffusion. This is investigating triggers that make the target image occur without any additional input from the attacker. And I also want it to be about a controllable amount of probability of when this will happen. So the previous work, as you can see, you have the training process, you have your random noise, it generates this is on a German traffic sign recognition database, to generate new images from that. If you were going to, it's very common in autonomous driving to have these essentially synthetic scenes that they can improve on because the amount of real-world training data, I mean, it's massive, but it's also good to have synthetic trained data. So this was a good example. And you have your glasses type trigger that they had in bad diffusion. But when you deploy this thing, only that clean noise is ever going to happen. So you're only going to ever get really the things that you actually wanted. You told it, generate me class 0, which corresponds to a 20 kilometers per hour sign. If you can't see it, that's what it is. And that's all that ever happens. But in our work, also in the previous work, they didn't allow class-based diffusion, bad diffusion, villain diffusion. You couldn't tell it what class. If you did a noise-based trigger, it was unconditional. So it would generate any number of any traffic sign. You had no control over it. So I also wanted the ability to say, generate me a speed limit sign, and it generate a stop sign because of the noise. And so in our case, it's actually hard to see, but I tried to highlight it a bit more. In the malicious forward noise in the training process, there's a little red square in the bottom right. That is the trigger. And you train it on that way. When you generate random noise, if it just so happens to generate some red pixels of some size in the bottom right-hand corner of your noise distribution, you will get your malicious target. And depending on the type of trigger, the intensity of the pixels, the size of that trigger, you can control the rate at which this model will then produce this. So that's what we're working on. And you can see a bit more of an example of these, a little bit more zoomed in. So you can compare the clean noise, the bad diffusion noise, our devil diffusion noise. They're all able to generate, though the clean obviously makes its clean image, but both ours and bad diffusion are able to generate the target images. And on the right-hand side here is an example a bit more of our 16 by 16 trigger, a bit more visible so you guys can see it. But as they go down to 4 by 4, 2 by 2, they become very hard to see. If you even just manually inspected the noise that caused this to happen, you might not even be able to tell that it's there by looking at the starting noise. So the target data sets that we did our analysis on, just for an overview, SAFAR 10, if you're not familiar with it, it's about 60,000 32 by 32 colored images representing these classes that you see on the screen. We actually use an up-res, use a different neural net to up-res them to 64 by 64 so that it could be a bit more a bit bigger of an image because 32 by 32 is such a small one. And then we use the German traffic sign recognition benchmark that has 43 different classes. And in both examples that you have here, here's like a swath of noise, generate 4 by 4, 16 images based off of this noise. And just looking at it, there's no way to know if any particular noise, like this is over thousands of different generations. And I grabbed one of them that said, okay, look, it caused the backdoor trigger to occur. It's difficult to see depending on where you're sitting. The traffic sign's in the bottom left. So without being able to control it, like the attacker did nothing here, just generate that noise, it's able to make the target that we wanted. So empirically, I won't break down every single part of this. Basically, there's two ways. What we need to do is make sure that this backdoor attack does not impact the actual performance of the model on its target task. So the way to do that is called FID, Fréchet inception distance. And that's how well, it's an attempt to say how well a generative AI system's images correlate with the target distribution. It's good enough. There are other methods as well that say, even though the distance is small, they may not be human acceptably good. There's different ways of doing, but it's the standard for now. And that's on the left side of the graph there, the graphs where the height of the columns represent the FID score. The lower the better because you want a lower distance. And the dashed red line is an unpoisoned FID score. So in some of our instances where the poison rate, the number of images that were poisoned, depending on the trigger size, are actually better. They perform better in the FID score than what an unpoisoned model does. And your black line is your backdoor rate. So depending on the trigger size, if the trigger is particularly small, obviously that small red square occurs more often in random noise than it does a very large red square. So they have higher backdoor rates to the point where 25% of the time at making a backdoor image, obviously that's going to impact your FID score, and that's unacceptably large. But if you want it to be very stealthy, you probably, depending on where you're sitting, you might not be able to see it. But on some of these ones, the very last one that I trained, I'm like, does a 16 by 16 trigger of this noise cause the target image to occur? And because I was getting 0%. And I'm like, well, let's generate 100,000 images. And big shout out to the Alliance, previously Compute Canada. They are supercomputers that we have access to as researchers. Without them, I would never have been able to generate that many images. And it's 0.006%. So out of that 100,000, I think it was the number, I got like 2 something, like that were actually the target backdoor. So if we made them even larger trigger sizes or more sophisticated triggers that would even be less likely, you could say I could make this entirely unacceptable image out of distribution occur 1 in a million times. And if we're generating millions of these, and as they're massive amounts, that will happen. That you will get that image. Someone will eventually get that image. And if it's in a synthetic data pipeline, maybe 1 in every 1,000, because who's going to look through every single image if this is used to train some downstream AI task? No one's really going to look through all those images. They might, but they probably aren't. They're probably used, discarded, so you can't even really go back and see what it had made previously. So some defenses. It could say don't use diffusion models, but that's obviously not particularly realistic. You can do a manual inspection. That would be if you're going to deploy things to be facing users, highly recommend that. As we've seen, even the incidental problems that diffusion models have are warranting some manual inspection of the things that they produce. You can also use, for example, Stable Diffusion has this like safety checker that will tell you whether an image has explicit imagery of certain types that it's generated before it gives back to the user. It's not great. For example, the top, there are false positives. The top right one is a false positive. I said this had something to do with female nudity. I don't know, but it just wouldn't have returned that to the user. The false negatives are a lot worse. I will caveat, if you're interested in this research, dealing with detecting of false positives can be difficult to look at the images that it creates. So, it's not for the faint of heart, and it's not particularly my area of research. And there are also some defenses for cleaning diffusion models. The authors of Bad Diffusion and Devil Diffusion did offer an approach that advanced neuron pruning that tried to figure out which ones were contributing more to this malicious, reverse diffusion process. But they found that it was highly hyperparameter specific, so you'd kind of have to already know ahead of time a little bit of how the backdoor was embedded. And another work that I tried, which is why I was late on giving this PowerPoint, sorry to the submission body, the one defense called Elijah, it tries to analyze, that's what this bottom right one is, it tries to optimize generating a trigger that will survive throughout the diffusion process. So they assume that if we can create a trigger that the next to last time step, right before it gives you your output image, there will be still some remnants of your original trigger. So for these examples, they're highly conspicuous, and so they do survive throughout the process. But there's two assumptions here. One, our trigger is very subtle. So in fact, the small red amount of noise is not very large, so it learns to diffuse instead just darker noise, because if you start with dark noise, the image is dark, so it's more of a similarity. It survives better than our trigger. And it also, you know, the next phase of the research is actually moving the trigger during the reverse diffusion process. So it's like if it changes color and it changes location, that assumption doesn't hold true anymore. So the defenses are definitely needs more research, and that's the next phase of what we'll be going forward with. But in addition, as I said, yeah, that's one of the main ones. But one of the other ones, again, this was kind of like a rabbit hole that I went down with my research, because I was like, I need to be able to create synthetic data with, you know, incorrect outputs at some rate. And I was like, there is no work on that for my pipeline, so I had to work on making that. What I am interested in is doing that, but within, as I said, 3D scenes. So there are really great models that were trained on permissive images, right? The people who created these textures said, okay, go ahead, you can use them for whatever you want, including AI training. And they're really good. So you can tell this entire scene, all the textures in that scene were generated from one of these types of models. So my next phase is to use this type of use this model, apply that backdoor to it, and then train like an object detection system on those textures and see at what rate and what probability can we have like an AI system, a neural network that can navigate a scene or detect objects in the scene that has learned a backdoor attack indirectly through the synthetic data from the diffusion model. So that's the next step as part of my thesis. So in conclusion, I want to leave a little bit of time for questions. Is that really, despite they're incredible. Like I don't want to scare people off from diffusion models. I think they're absolutely incredible, and I think they have a lot of potential in many genres, many themes, whatever people want to do. I think they're very helpful. I think artists eventually will be able to use them, although I am also agree that the way some of them were trained was not right. We're going to talk about that, not as a topic of this conversation, but I'm not going to apologize for the way that they were ever scraped, and I don't really believe in using those if I can avoid it. But the black box nature of these models means that they really aren't ready to be released into the wild without oversight, and I would caution against that. I would build it into some other more sophisticated pipeline with human intervention. So as a result, I highly recommend manual inspection of anything that's going to go out to places. And if you are able to encourage or support any research endeavors that work on both attacks, because I think these attacks are the least sophisticated these things could ever be. These are quite blunt attacks compared to some of the other neural net attacks that are out there. And the defenses are already very much lagging behind. So supporting people who are looking into the attacks and defenses is very important, especially if these models do end up coming on our devices as more and more big companies jump on the bandwagon, and they are able to create very unnerving images with these attacks are present in them. So we would really want to have a better safety checker on these things. So I very much appreciate, again, the chance to be up here and talk about something that I'm very interested in and that I'm working on. If you have any questions, I'll be happy to hear them. If you're looking to collaborate on this or the forward parts of the work that I'll be doing, I'd be happy to work with you. For some of the cybersecurity things, our lab is great. The cyber range is great. Reach out either by the link, or you can contact either of my two supervisors, without whom I wouldn't be here. So thank you. Thank you.